So here we are revisiting problem number 4.61 from tutorial 3. So this problem required us to find out Thevenin and Norton equivalent between node A and node B for this given circuit. So this can be, of course, carried out by applying mesh analysis in three mesh that exist here in this circuit, but that will of course lead to three simultaneous equations in three unknowns. So it's going to be a bit cumbersome to solve in this way. However, if we observe this circuit carefully, we note that this circuit is symmetrical about line A and A dash. That is left hand side and right hand side about A and A dash. They are a mirror image of each other. So we can exploit this symmetry to cut down the number of steps involved or the number of unknowns involved in solving this problem. Specifically, for the purpose of finding out the Thevenin voltage between node A and node B. So what we will do, we will modify this circuit, especially with respect to this 6 ohm resistor and this 12 volt source and this 2 ohm also, so that the entire circuit can be split into two independent halves about line A and A dash, and that will reduce the number of mesh from three mesh to only one mesh. That means it can be solved using only one variable. So here, first thing to note is that since circuit has left and right symmetry, that means node C and node A, they are going to be exactly at the same voltage. So that implies there will be no current through this 2 ohm resistor, and that says that this 2 ohm resistor can be removed, and that will have no effect on the voltage and current that flows through this circuit. Now once we have removed this 2 ohm, what we will be left with is this 6 ohm minus 12 volts and other components like here. So now our objective will be to modify this 6 ohm and minus 12 volt so that circuit can be split into two parts. So here we see that this 6 ohm here carries a current equal to 2I. One I coming from this 6 ohm, other coming from this 6 ohm. So the net voltage drop across this 6 ohm is going to be 6 into this 2I, that means 12I. So when we modify this 6 ohm, we have to ensure that net resistance through this path has to be 6 ohm. The net current flowing has to be 2I, and the net voltage should be 12I. So this can be done by dividing or representing this 6 ohm with the help of two parallel resistors like this. So here we see that each of the 12 ohm resistor, they carry current equal to I. So we see that these 12 ohm two resistors in parallel, they will be equivalent to 6 ohm. So we have same scenario as previous in terms of resistance. The net current carried by these two also remains 2I. So it is equivalent to previous one in terms of current also. And the voltage across each of these 12 ohm is going to be 12 into I, same as the previous scenario. So a single 6 ohm can be represented by parallel combination of two 12 ohms, each of them independently carrying current equal to I. Now we have to represent this minus 12 volt also in such a way that there is left and right symmetry in the equivalent circuit. So this can also be done easily by substituting the previous single minus 12 volt with help of two parallel combination of minus 12 volt sources, such that each of these two 12 volts sources carry current I. So now you can see that again the net current through this new equivalent sources also remains same as 2I that of the original case, and the voltage between this node and this node also remains minus 12 volts, same as the previous case. So we have now substituted the 6 ohm in series with minus 12 volt by this parallel combination of two resistors, 12 ohm and minus 12 volts. So now you can see that we can separate, or we can cut this circuit along A and A dash line, such that we have two physically separate circuits, and each will have exactly same conditions as the original one. So our original circuit boils down to this simple circuit containing only one mesh. So our objective of finding out the Thevenin voltage, which is the open circuit voltage between node A and node B, can now easily be realized by finding out this current I in this single mesh. So we can set up KVL in this mesh to find out that I is 1.2 ampere. So once we know I, we can find out the voltage drop across this 2 ohm resistor, which will be minus 2.4 volts. So this voltage, when gets added to 12 volt, gives rise to net voltage of 9.6 volt. So this is the Thevenin voltage between node A and B, found out very easily with the help of symmetry. So there's another way in which the original problem could have been attacked. Uh, this will still be simpler than the original problem solving using three variables, but a little bit more involved compared with the previous alternative using symmetry. So here what is done is that the centered mesh that existed in the original problem, consisting of 2 ohm, 6 ohm and 6 ohm between node A, C and D, can be substituted by a Y circuit consisting of RA, RC and RD, so that the third mesh, the central mesh in the original problem, gets eliminated and we have only two mesh. So we can invoke delta to Y conversion to find out these three new registers, and they are given by this 6 by 7 ohm and 18 by 7 ohm. So our original circuit gets modified to this circuit containing only two mesh. So now this can be solved by applying mesh analysis in these two mesh to find out the current I2, which will give us the voltage drop across 2 ohm, and then finally the net voltage between A and B, which will be Thevenin voltage. But here also we see that even after eliminating the central mesh, we still have circuit which is symmetrical uh, about this central branch. That means it still has left and right symmetry. So we can again invoke symmetry to split this circuit into two equal halves and then attack only one of them. So by uh, looking at the previous solution based on the symmetry, we find that we have to split these two resistors into combination of two parallel resistors. Similarly, this source also is a combination of parallel source. So if you do this, each of these resistors, they get doubled and the source remains same. So if we do that, we get one half of the circuit given by this. So 6 ohm becomes 12 ohm, 18 by 7 ohm becomes 36 by 7 ohm, and then we have our original minus 12 volt here. So we again have a circuit consisting of only one mesh. So once again we apply mesh analysis here to find out the current and the voltage across 2 ohm and finally the net voltage between A and B. So this is the second part after applying delta to Y conversion for the central mesh. And then we have our usual path 1 to solve the circuit obtained from delta to Y conversion in terms of I1 and I2. So by invoking symmetry, if it is there in the circuit, some of the analysis can be greatly simplified.